Few things seem as elegant and orderly as the periodic table. It's a masterpiece of logic, a map where every known piece of the universe has its proper place. But what if there's an element that just refused to fit? Something so unruly and confusing that it threatened to tear a hole in our perfect tapestry. Ever since the inception of the periodic table, chemists wrestled with elements that seemed to break all the rules. They were a maddening puzzle, chemistry's biggest nightmare, and it all started with Cerium. Hello and welcome to Meet the Elements, the series where I look at the stories of humanity through the lens of the periodic table. Today, we're talking about Cerium. Cerium is an interesting element due to its impressive list of practical applications, and because, for the longest time, it was kind of the last element chemists could accurately place. Even Dmitri Mendeleev himself couldn't figure out what was going on past Cerium. Like with many other elements, our story begins in Sweden, a place with a surprising amount of unique ores that don't really show up anywhere else in the world. Miners would come across interesting rocks with a reddish-brown color to them that were surprisingly dense. Wilhelm Hisinger, who had become intrigued by this strange mineral, reached out to Jöns Jacob Berzelius to figure out what it was. The pair were able to isolate an oxide from the mineral. Coincidentally, at almost the exact same time, the German chemist Martin Heinrich Klaproth isolated the same oxide from a different mineral. Working independently, both teams made the announcement. They had found a new Earth, the oxide of a new element. Berzelius and Hisinger named the new element Cerium, after the asteroid Ceres, which had been discovered just a few years earlier. The asteroid itself being named after the Roman goddess Ceres. However, they didn't really just find one thing. By finding Cerium in these minerals, they had unknowingly opened the door to one of the biggest challenges in the history of chemistry. Because here's the thing, Cerium never shows up alone. The ores that contain Cerium are a chemical clown car, and what chemists thought was a single element was actually tangled up with its siblings. The first insight into this chemical mess actually comes from one of Berzelius' own students, Carl Gustav Mosander. Mosander worked with ceria, the oxide of cerium, and discovered other elements hiding inside. Through a process of heating and dissolving the material with acid, Mosander found an entirely different element, calling it lanthanum. But Mosander wasn't done. He further separated the sample, finding a third element. He called this one didymium, meaning twin, due to its similarity to lanthanum. Of course, this name proved to be ironic when it was discovered that didymium was actually itself a mixture of two elements. The single discovery of cerium was now cracking open a door to a whole family of elements, and things were about to get real tricky. By the 1860s, Dmitri Mendeleev was assembling his iconic periodic table, a project to bring order to the elements. Yet this group of elements, which became known as the rare earths, resisted his attempts at classification. The pure elements all looked similar. They all behaved in almost the exact same way chemically, and separating them was a form of chemical torture, often requiring repeated operations only to end up with a minuscule amount of what was likely a still impure sample. Mendeleev himself was stumped. He tried to force them into his table with the transition metals, but they didn't behave like transition metals. But there was nowhere else even remotely close for them to go. For decades, the periodic table had a giant asterisk, a whole group of elements, starting with lanthanum and cerium, that were so similar they seemed to belong on top of each other rather than next to each other. They were a violation of the table's fundamental principle, that chemical properties would repeat after certain intervals. The element that was thought to be a simple discovery had instead created a gigantic mess that seemed impossible to solve. The key to solving this lanthanide nightmare was figuring out what made them so frustratingly similar. The answer was hidden deep inside the atom's structure. See, what determines an atom's chemical properties isn't in the nucleus, it's in the electrons. All chemical reactions are reliant upon what the electrons are doing. As quantum mechanics developed through the early 20th century, we gained a better understanding of what the electrons of an atom are doing, learning that they sit in defined orbitals around the nucleus, and even that there are different types of orbitals. Chemists discovered the lanthanides are what we call F elements. While most elements have their electrons added to their outermost orbitals, the lanthanides have their differentiating electrons buried within the layers of orbitals. This means their chemical personalities, the outermost shells they use in chemical reactions, are all virtually identical. For nearly 100 years, the only way to tell them apart was through brutal, repetitive chemistry. But two breakthroughs gave scientists a better way to see them. The first was spectroscopy, relying on the slight differences of orbital energies to identify elements. The second allowed scientists to finally get useful amounts of a pure element. During World War II, as part of the Manhattan Project, scientists working on the atomic bomb needed extremely pure materials, So they perfected the technique of ion exchange chromatography, which finally gave us the ability to easily separate the lanthanides. This was the game-changing key that finally unlocked the lanthanide puzzle. Chemists could now get their hands on pure cerium and its siblings, and they were about to discover that the very property that made cerium part of this chemical mob was also its greatest strength. The property that caused so much confusion was cerium's flexible identity, specifically its ability to switch between two oxidation states, having a charge of either +3 or +4. For modern materials scientists, this is a superpower. This unique quality makes cerium oxide a master of handling oxygen, and it's used to help keep the air we breathe clean. Inside the catalytic converter of almost every gasoline-powered car is a ceramic coated with precious metals like platinum and, crucially, cerium oxide. Its function is to act as an oxygen buffer. When your car's engine runs rich with too much fuel and not enough oxygen, there's a lot of toxic carbon monoxide and unburned hydrocarbons in the exhaust. The cerium oxide releases oxygen, oxidizing the pollutants into much less harmful products. A moment later, when the engine runs lean with too much oxygen, the cerium oxide springs into action again, absorbing the excess oxygen, storing it for the next rich cycle. This constant breathing of oxygen allows the catalytic converter to work efficiently under all driving conditions, destroying over 90% of the most harmful pollutants from a car's exhaust. But its role as an environmental hero doesn't stop there. Cerium is an important additive in catalysts used for petroleum refining, helping make the process cleaner and more efficient. It's also a focus of research for developing next-generation solid oxide fuel cells, which promise highly efficient, clean electricity generation. It's even being explored in agriculture, where cerium oxide nanoparticles may help improve crop yields, or the same nanoparticles can be added to diesel fuel to reduce harmful emissions in a similar way to a catalytic converter. Regardless of the use, it all comes down to that +3, +4 oxidation state pair of cerium. The journey of cerium is truly fascinating. Cerium's discovery kicked off one of the greatest struggles in chemistry's history. For decades, cerium and its siblings were a nightmare to try and organize, a chaotic mess that defied the beautiful order of the periodic table. They were a puzzle that seemed unsolvable. But as it so often turns out, the perceived flaw was actually a feature. Cerium's unruly nature was the very source of its power. The shape-shifting that baffled early chemists is what now allows cerium to act as a molecular lung inside our cars, inhaling and exhaling oxygen to keep our air clean. From a celestial namesake to a chemical curse, and finally to an environmental champion, cerium has completed a remarkable transformation. It's a reminder that sometimes the things that challenge our understanding the most hold the key to a better future. Thanks for watching. I actually have quite a bit of experience working with cerium oxide from my time as a grad student. I spent a good deal of time synthesizing nanoparticles and characterizing them with an array of different techniques. But now I want to hear from you. What part of cerium's story do you find the most interesting? Or I know there's at least a few uses of cerium that I left out. And if you want more stories about the struggles the periodic table holds, make sure to subscribe so you don't miss the next episode of Meet the Elements.